signals attached to power MOSFETs or power relays of some sort. They're connected in this form you can see right here in an H-bridge. What happens is you can model a electric three-phase motor as a set of inductors such as this, standard three-phase model. And what happens is each one of these inductors is connected to these phases, and you can end up, so you have this switching algorithm, and it can be inverted by it almost seeming as if it's going into a negative value, and this can be done by having it switch directions through the inductor. So it's not actually causing a negative voltage to occur, which could be harmful to a digital system. It's actually just reversing the direction. This was implemented on a field programmable gate array because as you can see here from like this example integral equation, the equations are very complex and they take a lot of processing power, and it would be very slow to implement them on something else. We chose a field programmable gate array to run this for our senior project because of this processing power and its deterministic performance. The purpose of this MATLAB project was to implement this functionality in MATLAB and demonstrate it using MATLAB. So as a result, the MATLAB code for this project is intentionally written not using the most efficient method at all. It's not written in a way that MATLAB would make efficient use out of it. It's written in a way that will accurately reflect how an FPGA will actually perform, these operations. So it actually ends up being a very complex project that had to be implemented because, as for an example here, we're using a 500 megahertz clock in the FPGA for the math modules. The DSP is using a 500 megahertz clock. So in MATLAB, we actually wanted to implement this directly, just as we've done with everything else. But this ends up meaning that MATLAB actually has to calculate all of these values for each one of these clock ticks, so to say. So there's a lot of functionality that was implemented or changed in order to do this. There are certain things that were done in order to make it so the MATLAB program could run more efficiently. That kind of takes away, or that it increases the efficiency of the script without actually making it too unrealistic. One of these so-called optimizations that I made was, there's this, if we have a startup situation, so say we're just starting, we're going to want to go through and calculate all these equations. In an FPGA, in reality, these equations would be calculated every single time. They would constantly be reevaluated each time something changed. But if the degree value doesn't change, or any sort of input that's necessary in order to conduct a space-vector pulse width modulation, it's actually not going to recalculate it. Even though this doesn't accurately reflect what an FPGA would do, this was done in order to optimize the MATLAB code. As another example of something that had to be changed, in Verilog, which is used to program field programmable gate arrays, you create a lot of constructs called state machines. In MATLAB, we tried to do the same sort of thing, and here you can see is a state machine I'm showing called the pattern generator, FSM, which stands for finite state machine. In order to implement this functionality, there's actually an operator that you have to use called the persistent, and this kind of models a so-called state register. And this has to be done because in MATLAB, since it's software, everything is a function. So you have to call a function when I want to run this state machine and make it execute its operations. In MATLAB, it's going to call a function which will create this state machine, and then once the function is completed and it will quote-unquote return these values, it will delete it. And you can't do that because that doesn't accurately model how a state machine operates. So in order to create a state machine in MATLAB, you have to create a persistent variable for the state register. And the same was done for these alpha, beta, gamma values, because those also must not change. They must stay the same as things are running.